Hey there students, Mr. Kigut here. In our video today, we're going to be continuing to expand our study of forces. Specifically in this video, we're going to look at the normal force or physical contact force and how we can start to solve for these forces using Newton's second law. So what I've got here is kind of our main force list that we've been working with, and why I have this up is just so we can kind of reference this as we go. We've already spent some time looking at sorry about that. Okay, so back to where we were. What we've got here is kind of our main force list. And what we've already done is gone through and looked at gravitational forces. We did some work with free body diagrams and applying Newton's second law to working with the force of gravity. Now what we're going to do is look at another one of our common forces, the physical contact force or normal force. So I'm going to come over to some open space and we're going to start to unpack what we call the normal force. Now, I am going to start refer to this force more and more as the normal force because of our abbreviation, which is F sub n. But remember, when we're talking about normal forces, we're looking at physical contact forces. So anytime there is physical contact between two objects. But, as I mentioned a moment ago, our abbreviation is F sub n. Okay, so we'll start, just like we talked about with our force of gravity, defining what is a physical contact force. We'll start to look at some of the equations, and then we'll look at a few scenarios involving contact forces. So, kind of first thing to mention, I already have it over here, but our notation is F sub n. The n there means normal. Okay? Now, what do we mean when we really say a normal force? Well, just very broadly, a normal force is a physical contact force between two objects. A normal force is just a physical contact force between two objects. Got my list of things here so I can make sure that we cover everything. Now, what do we mean when we say contact? Because when we start to look at problems, the word contact won't always be the word that shows up. There are oftentimes other words that imply contact that look a little bit different, but most of them are going to be things that you're pretty familiar with. So for example, what are some other words that we may hear as we're talking about problems that imply that there's contact? Now, this is a time where there was a class here. I would ask this out to the group. So what are other words that we might hear about that could imply contact? Well, some of the ones that are most common. Touch. An object touches another, right? So if you hear that word touch, that implies that there is contact between objects. Push. Yeah. So if one thing or one person maybe is pushing another object, or if one object pushes another, that's a form of physical contact. Other things we can hear are stand. Right? A person stands at rest on something, or an object is, usually that's for people, I would guess, but standing on something implies physical contact. Sitting, maybe to hit something, a little bit more violent. Not that we're advocating for those types of things, but something hits another thing, like a car hits another car, that sort of thing. Maybe you are holding on to something, right? Like a person holds a book. Again, that implies physical contact. You can see where we're going with this in that the list could be really, really long. We could sit here for another 10 minutes and list out all these different words that mean contact. But what I want to get across with this is we need to be able to see past only looking for the word contact and look at some of these other words. These are other words that will show up a lot that imply that there is contact between two objects. And again, anytime we have contact, there will be a contact force. Now, why do we call this a normal force? I think the idea of physical contact force seems more applicable, like, yeah, two things are in physical contact, there's a contact force. But why do we call it a normal force? Well, the reason we use the term normal force is because normal actually helps us see the direction of what's going on there. So normal, from a mathematical sense, and maybe you've heard this used in some of your math classes before, probably more so in the geometry side of things, but normal mathematically means perpendicular. Or if you have a normal line, it's a line perpendicular to another. So the reason we call this a normal force is this. the normal force, okay, Fn is always perpendicular to the contact surface. Fn, the normal force, is always perpendicular to the contact surface. Oh, got my pen there. Oh man, that rolled far away. Sorry. The normal force is always perpendicular to the contact surface. And we'll see this come up a bit more when we work with our free body diagrams. We've already kind of been seeing this quite a bit, but this is the reason we call this a normal force, because the direction of the force is always perpendicular to the contact surface. So take, for example, I'm going to push on the book, right? My contact surface would be my hand against the book. So my contact surface is that surface right here, and the force is perpendicular to that at a 90-degree angle. So it's pushing forward, right? That would be the direction of that normal force. As well, when the book is sitting here on the table, and we'll talk about this one here in a moment, right? The table is our contact surface. The normal force is perpendicular to that. So that's why we use this word normal, because it tells us the direction of that force. Okay, so we have an idea of what this normal force is and why we call it a normal force. We know the abbreviation. What else is going to be relevant here? Well, do we have an equation for this? Think back to what we did with the force of gravity, right? We have an equation for a gravitational force. What about for normal forces? How do we calculate these? Well, something that's important, and I'm going to put a star by this, because it's an important aspect of these forces. Not that everything's not important, but this is particularly important. There is no set equation for a normal force. Sad face, right? Because, again, if we have an equation, then it makes life a little bit easier. We take our numbers, put them in, solve for what we can. But here we don't have that. So, if we don't have an equation, how do we figure out how strong this force is? How do we know? Well, if we have no set equation, that means we can solve for Fn. You know, we have to solve for Fn using Newton's second law. Or, I'll put this in parentheses, or Fn will be given. Those are the only two ways we can solve for a normal force. Either the force value is just given to us, maybe the problem statement or maybe the system we're looking at will know that normal force just right off the bat. But oftentimes to solve, we're going to use Newton's second law. If we don't have an equation for this force, and this will actually be a kind of a pretty consistent theme, if we don't know what a force value is, and we don't have an equation for that force, we're going to have to use Newton's second law. That's the equation that helps us figure out what's going on with our sum of forces, all the forces together. So, if we're asked to solve for a normal force, that means we're going to, most of the time, use Newton's second law. Again, there might be a few cases where it will be given, that's why I put that in parentheses, but most of the time we'll have to use Newton's second law to solve. Okay, so let's take a scenario here, right? Something that would be relatively common dealing with a normal force. Okay? So, we're going to do a few of these, kind of apply what we know about normal forces. So let's say scenario number one. Let's take the book on the table. This book that we've been dealing with quite a bit. It's taken a little bit of abuse over the last couple of days of me dropping it. But let's take the book on the table. Okay? So let's say we want to analyze the forces on the book. Specifically, let's say we want to solve for Fn. Solve for Fn. That's what we're trying to do here. Now, as we talked about just literally seconds ago, we don't have an equation for that normal force, but we can solve for it using Newton's second law. So how would we go about this? Well, our process to use Newton's second law always begins with a free body diagram. What are all the forces acting on our object? So, free body diagram. Our object is our dot. Okay, what forces are there? Well, we're on or near Earth's surface, so we'd have a gravitational force. from the earth on the book, F sub g. And then we have a contact force. Now, we're not going to do this really ever. In fact, I don't even want you to write this down in your notes. I'm just going to do it so you can see that. I'm going to put a dotted line here to show that that's representative of the table. Okay, that's not a force, that's just showing where the table would be in our model here, this diagram. Now again, normal means perpendicular. So that is, again, I'm trying to reemphasize why we call that a normal force, because that direction will always be perpendicular to our contact surface. And that's something I want us to see. Again, you don't necessarily need to write that down. I don't want that to confuse you too much. You don't have to put the dotted line in there for the table, but I do want you to see, again, that's why we call it the normal force. And again, that can change depending on if we're on flat ground or on some kind of an inclined surface, right? Okay, so we've got our free body diagram. Now let's go to Newton's second law. Okay, so Newton's second law, sigma F, sum of forces is equal to mass times acceleration. Now, in our case here, we're not really looking in the x direction, so I'm going to just do this for the sake of my example. In the x direction, sum of forces in the x is equal to 0, because there are no forces in the x, and therefore there's no acceleration in the x direction. Okay, so what about in the y direction? Well, we'll go sum of forces in the y is equal to mass multiplied by acceleration in the y. Okay, so how many forces do we have in the x direction? Well, sorry, the y direction, we have two. One that's a normal force and one that's a force of gravity. Okay, so the way I would set this up is I would have two forces and I would add them. But remember, when we add vectors, they are vectors, meaning they have direction. So I have Fn, my normal force, plus my force of gravity, but that's downward. So I'm going to write minus F sub g is equal to mass multiplied by acceleration. Okay. So a few things here. In the future, and what you may see some people do, and I may even do this at the same time, is we can also rewrite this as Fn. Rather than plus a negative force of gravity, we can write this as minus F sub g. Because we are summing them up, we are adding them, but since one of our forces is negative, we can write Fn minus Fg. I like to always start with a plus and negative, so I can always show that I'm summing them up, but some of the forces we sum up will be negative. Now, as the book sits right here, is it accelerating? Is it speeding up, slowing down? No, it's just here at rest. So, that means, well, the mass, don't we know the mass of the book? Haven't we dealt with this object before? I think so. The book had a mass of 2.46 kilograms. So if I put that value in, the book's mass is 2.46 kilograms multiplied by 0 meters per second squared. Well, what does 0 multiplied by any number give us? Well, just 0. So I end up getting that my normal force, Fn, minus Fg is equal to 0. Okay, so now I have, well, if I can figure out what my force of gravity is, I can then show that, well, I can add Fg over to this other side of my equation. So I get, overshot it there, I can show that my normal force is equal to my force of gravity. Now, I do want to emphasize, this is not always going to be true. This is true in this specific scenario. Normal forces are not always equal to gravitational forces. That just happens to be true based on what the sum of the forces is doing here. So, I really want to caution you, do not internalize this as those two forces are always and forever equal. There will be several examples where those forces are equal, but we're going to look at one here in a moment where they're not. Okay, so how do we find what our normal force would be? Well, we can use our equation for force of gravity. That is m multiplied by g. Remember, this equation doesn't tell us direction. Okay, so I've got just finding the magnitude of that force. So mass is 2.46 kilograms. And g for the Earth, 9.81 meters per second squared. In fact, we kind of already did this in our last example, so you may recognize this number, 2.46 multiplied by 9.81. So I get F sub g is 24.1 newtons. And now I'm showing that my normal force is equal to my force of gravity. So my normal force should equal 24.1 newtons. And there we go. There's how we find our normal force. Okay? So, good example of how we go about solving for a force when we don't have an equation for that force. We have to use Newton's second law. Okay, so good example of kind of a setup like this where we have no acceleration. So now what we're going to do is kind of transition over and look at maybe another example with a different object, and we'll try and look at something where there is an acceleration. Specifically one where the acceleration may not just be an object in free fall. Okay, so our next scenario, we're going to stay with normal forces for a moment. We'll call this, what do we say, was that scenario 1 for this setup? Let's see, losing my numbering system. Okay, so let's say, get over there. There we go. Scenario number 2, we're going to look at an elevator system. Okay. Now, this is a relatively classic type of problem in the physics world. And this will be a good example of using what we know about forces, free body diagrams, Newton's second law. But specifically, this will help us look at a system where there is an acceleration. Okay? So, here's what we've got. Okay? Let's say we've got a person standing in an elevator. Where am I? I want to make sure I have all of my things here. Okay, so kind of part 1 of this, let's say we have a person standing on a scale in an elevator. Kind of a very specific type of scenario. Person standing on a scale in an elevator. So let's get a little bit of a picture here. So we've got, let's say our elevator here. I'm just going to draw this as a box. And then we've got a scale here. Just going to put scale. Okay, so we've got a person, so we've got an elevator, we've got a scale there. And let's say we have a person standing on that scale. I'm sure that this box is a little bit wonky. Sometimes when I get close to the screen, I have a hard time keeping the lines nice and straight, so I'll adjust that a little bit. Okay, so we have a person standing on a scale in the elevator. And let's say this person has a mass of, let's go maybe about, say, 5, let's go about 50 kilograms. So mass of the person, let me just put this under. So mass is 50 kilograms, mass of the person. The person is going to be our kind of main object here. Okay, so here's going to be our question, and we're going to look at this a couple of different ways. So here's our question. When at rest, so let's say that this whole system is at rest, so a person just walks into the elevator, stands on the scale. Don't know why there'd be a scale there, but it fits our scenario, and I'll kind of unpack that a little bit more. But say a person goes in, stands on the scale at rest. So when at rest, here's our question. What is the scale reading? Person comes in, stands on the scale. What is the scale reading? Okay, now let's unpack that a little bit. A scale is going to measure a force. Typically, we think of scales as measuring our weight. But what the scale is actually measuring is it's measuring how much force the scale has to push on you with to keep you at rest. Because if the scale doesn't push you up, well, you're just going to step and break through the scale and accelerate downward. But that's not really most of our experience with the scale. Most of the time the scales are strong enough so that when we step on them, they can support our weight. Okay, so what is the scale reading? Well, to clarify, what the scale actually measures, scales measure contact forces, or what we call normal forces. The scale is measuring how much force is applied back onto you. It's kind of an indirect measurement of our weight. So the scale is going to measure what our weight would be kind of indirectly. So how do we go about setting this up? Well, as we talked about, with normal forces, we need some equations to be able to figure these things out. So the equations we've been using have been, well, Newton's second law. So let's start with that. So let's get an idea of what the forces are on that person. So we've got on the person, so a person is our body, our object here. We would have a gravitational force, assuming we're on or near Earth's surface, which we are here. And then we have a normal force from the scale onto the person. And that's the force we want. We want to know what is the scale reading, meaning what is the normal force onto the person. And as we talked about, for normal forces, well, we need to use Newton's second law to figure that out because we don't have an equation for those. Okay, so now that we have our free body diagram, let's go to Newton's second law. Okay, so we've got the sum of forces on an object is equal to the mass of the object multiplied by the acceleration. Now, remember, forces are vectors, so we generally have to account for the x and the y direction. Here, in the x direction, well, there are no forces here. So the sum of forces in the x would be 0, because there are no forces there, so our acceleration would be 0. Which hopefully makes sense. We're not going to be accelerating right or left. We're only going to be accelerating up or down, possibly. But here we're at rest. Okay? But for the most part, we can ignore the x direction because there are no forces in that direction. So now let's go to the y direction. Sum of forces in the y is equal to mass times acceleration in the y. Now, this is going to look almost identical to the problem we looked at a moment ago with the book and the table. So here we have two forces. Normal force, which is up, that's the one we're after, Fn, plus our force of gravity, but that's negative, so plus a negative Fg is equal to mass times acceleration. Okay, so then we can simplify that down. Fn minus Fg is equal to, well, what's our mass for the person, assuming this person is us? Mass is 50 kilograms. Acceleration is 0 because we're at rest. So 0 meters per second squared. And then, well, 0 multiplied by any number is just 0. So I have Fn minus Fg is equal to 0. Okay, so now if I just find what my force of gravity is, I can finish this out. So force of gravity, we have an equation for that. I'll kind of do that over here on the side. F sub g is equal to mass multiplied by local acceleration due to gravity. So mass was 50 kilograms. G for the Earth, 9.81 meters per second squared. So I can do the math here. 50 and 9.81 should be a little under 500. And I get about 491 newtons. 491 newtons. Okay? So then I can bring that value over here into Newton's second law. So I get Fn minus 491 is equal to 0. And then to finish things out, I can add 491 to the other side of our equation. Plus 491 newtons to show that the normal force, or what the scale would read, is 491 newtons, or approximately about 110 pounds. So maybe a little bit of a lighter person here. Wouldn't be me, but anyway, don't need to go down that path. So our normal force, what the scale would be reading, is 491 newtons. So hopefully this gives us, again, another good example on how we go about solving things. Okay, so we've looked at two problems where the object is at rest, no acceleration. But what happens if the system does accelerate? Like, what if we're standing in the elevator and all of a sudden the elevator starts to speed up, going up? What would happen with what's going on here? So we're going to take this same problem and we're going to extend it to look at now a little bit of a different scenario. So here's our next question. Now, same idea. What would the scale read if the elevator accelerated upward at, let's say, 3 meters per second squared? What would the scale read? Now, I want you to think for a moment, how would you feel, just maybe physically, if the elevator started to move upward? We've probably all been in this situation before. You stand in the elevator, it starts moving upward. Well, you might feel as though you kind of are getting pushed down just a little bit, right? And we can unpack that. Think about Newton's first law. Objects at rest want to stay at rest. Objects in motion want to stay in motion. unless they're acted upon, right? Stuff keeps doing what it's already doing unless it gets pushed around. So if I'm at rest, my body doesn't want to change. It's wanting to stay at rest. But if the elevator starts accelerating upward, I may resist that. That's my inertial response, my resistance to that change. So I may feel like my body's kind of getting pushed down. It's not actually getting pushed down, it's just my body's resisting change, so it feels like it's getting pushed down. So what may happen here is it may feel like I'm getting pushed down, so it may appear that I'm feeling a bit heavier, like I'm getting pushed on. And we'll see if the numbers actually support that. So in this case, what's going to change about our forces on me if I'm just standing there on the scale? Well, according to my free body diagram, what are my numbers here? According to my free body diagram, are the forces really going to change? I still would have a force of gravity on me, which we found a moment ago, and I would still have a normal force on me. But now, it may not be the case that those forces are equal. Now, one thing we didn't talk about a moment ago, but now I'm realizing we probably should have mentioned that. Those forces, we just showed two examples where our normal force is equal to our force of gravity. Are those forces pairs, according to Newton's third law? Because they do appear to be equal and opposite. I'm going to drive this point home again and again and again and again as much as we can. Those forces are not pairs because they're not the same type of force. Contact force and a gravitational force. Those forces are equal. They're both equal to 491 newtons, and they're opposite in their directions. One's upward, one's downward. But they're not pairs according to Newton's third law, because Newton's third law is not about equal and opposite. It's about forces always existing in pairs. We can have one of those forces without the other. Gravity can still be pulling on me, even if I'm not touching the scale. Right? I can have one of those forces without the other. Forces either exist together or not at all. Those forces are not pairs. If you want more information on kind of the third law applications, we're not going to unpack as much of that here. Go back and watch some of the previous videos. Right? But again, those forces are not pairs just because they're equal and opposite. Lots of forces will be equal and opposite. That doesn't mean that they're pairs. Okay, so now, if we're accelerating, well, I still have these two forces. There aren't other forces there, but there may be some different values that go on with those forces. So now if we apply Newton's second law, well, sum of forces is equal to mass times acceleration. Just like before, we can pretty much ignore the x direction here. So I'm just going to go straight into the y direction. Sum of forces in the y is equal to mass times acceleration in the y. Okay, so I've still got my two forces here. Normal force is still positive. Force of gravity is still negative. Okay, so I have Fn plus a negative. So I'm going to write minus Fg. I'll shorten it up just a little bit here. Is equal to mass times acceleration. Okay, now what things are going to stay the same here? Well, my force of gravity should stay the same because our force of gravity is just how strong the Earth pulls on me. The Earth's not pulling on me stronger or weaker just because the elevator accelerates. Like, that's still going to stay the same. And think about the pieces of that equation. M stays the same, my mass is the same, and G for the Earth stays the same. We found this a moment ago. M times G gave us 491 newtons. That's going to stay the same here. I'm going to put my mass in here in just a moment, and now I'm going to put in my acceleration, positive 3. So I'm going to write down Fn minus 491 newtons is equal to my mass, 50 kilograms, multiplied by an acceleration of 3 meters per second squared. So Fn minus 491 newtons is equal to, well, 150 multiplied by 3, that's going to give us positive 150, and kilograms multiplied by meters per second squared, those are the units that make up a newton. So now, to find my normal force, I can add over 491, and 491 plus 150, I get Fn, that's going to be about 641, I believe. Let me just double check. Oh, 491 plus 150, yep, 641. So 641 newtons. So the scale is now going to read 641 newtons. Does that mean I actually weigh 641 newtons? No. It means that I might appear to weigh, I might feel as though I weigh a little bit more because my body's resisting that change in motion. And this phenomenon, this idea, is something that we oftentimes refer to as apparent weight. Right? So that normal force, right, expresses something that we call apparent weight. Meaning, it's how much our weight might appear to be, how much we experience it to be, even though that's not actually the weight of my body, it's how much it appears to be because I'm accelerating. Okay? And again, if I'm accelerating, it can appear as though I have a different weight than I actually do. The same might be true, well, consider when I'm moving, and then the elevator might eventually come to a stop. In fact, it should eventually come to a stop, I hope so. When you do, maybe if you're anything like me, when I was younger, I'd get to the top, and then all of a sudden you feel as though you feel a bit lighter, right? That's because you have an acceleration, which is going to change how your weight appears to feel. So, when we're asked these questions about apparent weight, if I'm asked to find apparent weight, what I'm really looking for is apparent weight is my normal force. Okay? So if you're asked that question in the future, that's what we're looking at. And this oftentimes comes in when we're looking at a system that is accelerating. Okay, so hopefully this is giving us some good applications with using Newton's second law with normal forces, both when we're at rest and now when we're accelerating. Okay? We could actually look at this if we were, well, slowing down, we had a downward acceleration, or if we have an upward acceleration. We could look at this a lot of different ways. It may change what our normal force would be, our apparent weight would be, based on our acceleration. So if we have some time left, which I'm going to check here in just a moment, we're going to look at one more example and what we do in the second law and a normal force. Okay, let's see. How are we doing? Oh, yeah, we're great. Okay, pick back up here in 3, 2, 1, go. Okay, so there's now kind of one more thing I want to touch on. We've looked at when the object is at rest. We've looked at when the object is accelerating. What about maybe one last scenario with the elevator? What about this? Question 3, if you will. What would the scale read? I'm just going to kind of shorthand this. Scale reading with a constant velocity. What would the scale read if I was moving at a constant velocity, let's say of 4 meters per second? I'm going to make this kind of tricky. What would the scale read? Okay, so this would simulate, I get in the elevator, I stand at rest for a few seconds, get my reading on the scale. Then, well, I start to accelerate, so maybe I accelerate for a few seconds, and then the elevator comes to a nice constant velocity. You know, maybe I'm going up to my penthouse apartment. Real fantasy scenario here. But let's say I accelerate for a few seconds, and then I get to, well, just moving at a constant velocity, 4 meters per second. Okay, so there, my free body diagram is going to look pretty much identical to my last two scenarios. I'd have a gravitational force, Earth pulling on me, and then a normal force of the scale back onto me. Okay, so Newton's second law, the sum of forces is equal to mass times acceleration. Sum of forces on an object, all forces together equals the mass of the object multiplied by its acceleration. Okay, so again, just like in the last two scenarios, nothing in the x direction, no forces there. So I can ignore those, and I'm going to go straight to my forces in the y direction. Sum of forces in the y is equal to mass multiplied by acceleration in the y. Okay, so what forces do I have? I've got a normal force and a force of gravity. Very similar. The left side of my equation is going to look pretty much identical because I'm summing up the same forces. The numbers might look different, but the forces that we have there are the same forces. Right? I have a normal force upward, Fn, plus a negative, so minus a force of gravity, is equal to mass times acceleration. Okay, now, I threw the number 4 in here to be particularly confusing. If you are not careful, and I've made this mistake myself before, when I was learning some of these things, if you're not careful, here's what you have a tendency to do. You may read that and think, oh, I'm going to plug in 4 for my acceleration. As we've talked about, physics is a lot about the subtleties. If we're not careful, it's very easy to take a number, throw it into an equation, get an answer, and think that what we're doing there is correct. We have to be very careful here. Newton's second law doesn't say the sum of forces equals mass times velocity. It says the sum of forces equals mass times acceleration. So what is our acceleration here? Well, constant velocity. What does that phrase mean? Well, velocity is a measurement of how fast an object moves with its direction involved. If our velocity is constant, that means we are moving at the same speed in the same direction. Acceleration, again, measures a change in velocity. So, if and when you hear the term constant velocity, and I'm going to come down to another space because I'm going to write this in big red text because it's very important. Constant velocity means we have no acceleration. Constant velocity means acceleration is 0. Maybe move this whole thing down. Constant velocity means we have no acceleration. If you ever hear the term constant velocity, even if you're given a number for that velocity, that number may as well be irrelevant. It does not matter what the velocity is if it's constant. Because the thing we care about is whether or not we are accelerating or not, right? Newton's second law says that the sum of forces equals mass times acceleration. We're not looking at how fast we're moving, we're looking at if we're accelerating. So, Fn minus Fg, in this case, is equal to mass, 50 kilograms, multiplied by 0 meters per second squared. So I get Fn minus Fg is equal to 0 because we have a constant velocity. And that tells us the scale should read the same as it does when I'm at rest, or when the elevator's at rest. Right, our force of gravity, we've already found that was 491. So Fn minus 491 is equal to 0. I add that over to show that my normal force, which is the scale reading, is 491. So no matter if we have a constant velocity up of 4, a constant velocity down of 8, anytime you hear constant velocity, that means our acceleration is 0, which also means, therefore, that our sum of forces has to be 0. Okay? Because remember, as we've talked about with Newton's second law, right? The sum of forces equals m times a. Okay? Whatever the direction is of our acceleration is also the direction of our sum of forces. So if our acceleration has 0 direction, that means our sum of forces is 0. If our sum of forces is positive, if our acceleration is positive, that means our sum of forces has to be positive. If our acceleration is negative, that means our sum of forces has to be negative. Right? Look back at what we did when the system was accelerating. Right? When the system was accelerating, we had a positive acceleration. That was down here. We had an acceleration of positive 3. And what was our sum of forces? Well, our sum of forces would have to be positive, right? We had something like 641 minus 491. So we'd get a positive sum of forces and a positive acceleration. And again, the key here is that the direction of our acceleration has to match the direction of our sum of forces, because those are our only two vector quantities. If acceleration is 0, our sum of forces has to be 0. If our acceleration is positive, sum of forces is positive. If our acceleration is negative, sum of forces is negative. And whatever direction our acceleration is, our sum of forces has to match. And even if our acceleration is 0, our sum of forces has to match there. Again, don't want to overload with too much information here, but I really want us to get to some of those subtleties because those will be very important when we talk about Newton's laws of motion. So, we're going to stop here. This covers a lot of the main things we want to see with normal forces. I do want to caution you, normal forces will not always be equal to a force of gravity. We've seen some examples here where it is, and some examples where it's not. Do not let that saturate in your mind that Fn always equals Fg. That's not the case. Sometimes they'll be equal, but there will be several scenarios where they're not. Okay? And again, in order to find Fn, always go back to Newton's second. Excuse me. Always go back to Newton's second law. That's what we must do in order to find that force. So this covers most of what we want with normal forces. In some of our following videos, we'll look at some of our other forces, things like frictional forces and tension forces, to finish out our list. And as always, if you have questions, please let us know. Other than that, good luck.